Space is a vast and mysterious frontier, and quantum physics plays a surprising role in understanding and exploring it. From the behavior of particles near black holes to the transmission of information across the universe, quantum mechanics helps explain phenomena that classical physics alone cannot. In this video, we will explore how quantum physics is applied in space, why it matters for both science and technology, and the fascinating discoveries it enables. One of the most important applications of quantum physics in space is in understanding the early universe. The Big Bang produced conditions of extreme density and energy, where quantum effects dominated. Quantum fluctuations during this period created tiny variations in density that eventually grew into galaxies, stars, and planets. These small quantum ripples are preserved in the cosmic microwave background, the afterglow of the Big Bang, and studying them helps cosmologists understand the origin and evolution of the universe. Quantum physics also explains the behavior of particles near black holes. According to quantum theory, black holes are not completely black. Stephen Hawking predicted that quantum effects at the event horizon cause black holes to emit radiation, now known as Hawking radiation. This phenomenon arises because particle-antiparticle pairs constantly form and annihilate in empty space, and near a black hole, one particle can escape while the other falls in, allowing the black hole to slowly lose mass. Hawking radiation is a profound connection between quantum mechanics, gravity, and the structure of spacetime. Another striking example is quantum entanglement over long distances in space. Experiments have successfully entangled photons and transmitted them between satellites and ground stations, sometimes across hundreds or even thousands of kilometers. This demonstrates that entanglement is not limited by distance and opens the door to a global quantum communication network, potentially enabling unhackable encryption and secure transmission of information across the planet, and even to space stations or future colonies on the Moon or Mars. Quantum sensors are another exciting application. Space missions often require extremely precise measurements of gravitational fields, magnetic fields, or acceleration. Quantum devices, such as atomic interferometers, exploit superposition and interference to detect minute changes with unprecedented accuracy. These sensors can improve navigation for spacecraft, monitor Earth's gravitational anomalies, and even detect gravitational waves with extreme sensitivity. Quantum mechanics is also crucial for understanding fundamental particles and forces in space. Cosmic rays, neutrinos, and dark matter interact in ways that require quantum theory for accurate prediction. For example, neutrinos traveling through the universe oscillate between different quantum states, a phenomenon that only quantum mechanics can explain. Studying these particles helps scientists probe the structure of matter and energy on cosmic scales. One futuristic application is quantum computing in space. Deploying quantum processors on satellites or space stations could enable real-time processing of massive data streams from telescopes and sensors. Quantum algorithms could simulate complex astrophysical phenomena, optimize satellite networks, or accelerate discovery in astronomy and planetary science. Space-based quantum computing could complement ground-based research and expand our ability to explore the cosmos. Quantum physics also intersects with fundamental questions about spacetime and gravity. Attempts to unify quantum mechanics with general relativity, a field known as quantum gravity, often focus on extreme environments like black holes or the early universe. Observations of cosmic phenomena provide real-world laboratories to test theories that aim to merge these two pillars of physics, giving insight into the nature of reality itself. Even navigation and timekeeping in space rely on quantum effects. Atomic clocks, which use the precise energy transitions of atoms, are essential for GPS satellites and deep space communication. Quantum mechanics ensures these clocks maintain incredible accuracy, which is crucial when navigating millions of kilometers through space. In simple terms, quantum physics in space is about applying the rules of the very small to understand and explore the very large. It connects subatomic particles to galaxies, black holes, and the universe as a whole. Quantum principles explain phenomena that classical physics cannot, enabling technologies and experiments that expand humanity's reach beyond Earth. The study of quantum physics in space also highlights how intertwined the universe is. Tiny fluctuations in the early universe shaped the galaxies we see today. Entangled photons link locations across continents or even orbital distances. Quantum effects influence the behavior of stars, black holes, and fundamental particles. Understanding these connections gives us a more complete picture of the cosmos. Finally, quantum physics in space is not just theoretical. Experiments on satellites, space telescopes, and space stations have already confirmed quantum principles in environments far removed from Earth. These experiments push the boundaries of science, testing the limits of quantum mechanics and offering practical applications in communication, navigation, and sensing. Quantum physics in space shows that the rules governing the very small have profound consequences for the very large. By exploring these principles beyond Earth, scientists are uncovering new insights about the universe, developing advanced technologies, and preparing humanity for a future among the stars.